All right, we're picking up where we left off. This is number 3 for 2019 FRQ, page 11. Guys, give me 1 second. Just to recap part A, we have to find the missing portion that's not shown in our graph. So the full region from -6 to 5, which includes the part that's revealed and the part that's hidden, we can split up into 2 separate regions. -6 to -2 is the region that we don't see. But then we can pick up right at -2 and go from -2 to 5, which is the portion that we do see. This we can figure out just by looking at the shaded region between the graph and the x-axis. And all these are going to be formed from geometric shapes or combinations of geometric shapes. So I have a triangle here, triangle below, so 1/2 minus 1/2. I have a -1/4, positive 1/4, right? These are all found by 1/2 base times height. I got a square here, that's an area of 1. I got a triangle here, that's area of 1 as well. 1 plus 1 is 2. And then this is not a geometric shape by itself, but it can be found by involving 2 geometric shapes that we do know the area of, square and a quarter circle. So imagine taking the square here, a 3 by 3 square, and then subtracting out this quarter circle, and what you're left with is this region here. So square 3 squared, quarter circle is 1/4 pi r squared, and we get 9 minus 9/4 pi. So if we make our substitutions here, we know this portion is equal to 7. We know this is still the unknown that we're looking for. And I can just add up all these terms, all these areas that I want to involve. So 1/2 minus 1/2, -1/4 plus 1/4. This is 1 plus 1, that's 2. A lot of these will cancel out. This is 11 minus 9 pi over 4. I'm going to move it over to the other side. So 9 pi over 4 minus 4. Part B, we want to evaluate the definite integral All this parentheses may make you feel like as if you got to go through one big rule, you got to go through one big U substitution, but you see that these are two separate terms separated by a plus sign, and there's nothing outside the set of parentheses. So we can completely drop the parentheses and treat these like two separate definite integrals. So that's what I'm going to do with part B here. Each can be its own individual rule. So this we can apply using first theorem. F prime will rise up to f of x. Plug in upper bound, lower bound, right? Integral of f prime is just f of b minus f of a, and we can have that 2 tag along. But this is something different. This we got to go through a power rule, right? The integral of 4 becomes 4x. Okay, so let me show you the work of the process that we go through. F prime turns into f of b minus f of a, the 2 tags along. F of 5, we look at our graph. F of 5 is 0. F of 3, we look at our graph. Looks like it's a point that's hard to identify, but we know what that point is because that's provided for us at the beginning of the problem. They do tell us what the y value is. The y value is 3 minus root 5. 2 is still on the outside to distribute. And then off to the side, we have to solve the separate antiderivative. 4 becomes 4x. Work in our upper and lower bound. Upper bound gets inserted first. 4 times 5 is 20 minus parentheses 4 times 3, which is 12. 20 minus 12 is 8. So we have the numeric result of the first integral. We have the numeric result of the second integral. Distribute, combine like terms, go as far as we can go. We get 2 plus 2 root 5. Okay, any questions with part B? Good. Okay. So part C. The function g is given by g of x from -2 to x. Find the absolute maximum value. So this is how we're going to be building. So we know that there's this relationship here. F is really sitting at the derivative level of g. So we know that this f is really the g prime. Okay, that's what this is telling us, right? That f is sitting at a level below g. So it takes the integral of f to make it equivalent. So f is really my g prime. Okay, find the absolute max. So absolute max, we have to involve extreme value theorem. On the interval from -2 to 5. Well, let's create a sign line and see if we can find our relative max and relative min. So this is our G prime graph from -2 to 5. We know that anything above the x-axis represents positive slope. Anything below is negative slope. Anything on the x-axis is slope 0. So let's see where my critical points are. Critical points are my x-intercept, so I have one at -1. We also have another one at 0.5. Okay. We see that between -2 and -1, our G prime graph is clearly sitting above the x-axis. That's going to mean our graph is going to be rising. Between -1 and 1/2, my derivative graph is clearly sitting below the x-axis, so negative slope. And then between 1/2 and 5, it's all sitting above the x-axis, so positive slope. We know we see a relative max at -1, a relative min at 1/2. We're trying to find the absolute max, so we can ignore relative min. There's no chance that a relative min could ever be the highest point on the graph. So we only have to worry about endpoints and the one critical point. Okay, so we're going to test x is -2, -1, and 5. Okay, so we'll test those points against our g of x function. We haven't found any area yet. Well, here that we haven't moved at all. So we're starting at -2 and then -2. There's no area to be found. My area is going to be 0. We just follow the rule from -2 to -1. So the area of the graph between -2 and -1, that's just going to be positive 1/2. Okay, we'll test the other endpoint, g of 5. So g of 5 is the definite integral from -2 to 5. So from -2 to 5 is this whole region, which we can add up again, but I think we already kind of found it, right? We found it from part A. Yeah, 11 minus 9 pi over 4, right? That's the area from -2 to 5. So 27 over 4, that's around 7-ish. 11 minus 7 is around 4. So comparing these values between 0, 1/2, and 4, we see the highest value is 4, so the absolute max must be at g of 5. Or it's asking for the absolute max value, right? So find the absolute max value. So absolute max value is okay, part D.
Mr.
Evaluate the limit. Yes, question.
So you don't test 1/2 because you know it's a minimum based off like your
that's
derivative
right.
side line? Okay.
Yeah, I mean, if it says find the absolute max and min, then I would go through in trouble and use 1/2. It wouldn't be wrong if you tested 1/2. It's just that we can save some time if we know that it has no chance of being an absolute max.
Okay.
Yeah. Okay, part D is asking us for to find the limit. Now, when I saw this, my instinct was just to say, okay, this is probably a L'Hopital's rule, which it could be, but we never want to assume L'Hopital's rule before we actually evaluate, right? L'Hopital's rule requires something in particular. It requires a 0 over 0. So but even if it's L'Hopital's rule, you got to go through and at least substitute and evaluate the limit at that point. Okay. So if we do L'Hopital's rule, even if it is correct, and if you didn't go through the initial checks, that's going to potentially result in some lost points. But in this case, we don't, we may assume L'Hopital's rule, but we don't know it until we actually see what this produces. So let's enter 1 in for x, see where that leads us to. Okay, so 10 to the first power is 10. F prime of 1 is asking for the slope of the F graph at 1. The slope of the F graph at 1, that's part of this line. This line segment is up 2 over 1. That's a slope of 2. Over F of 1. F of 1 is 1. That's the y value of my F graph. Now, arctangent of 1, let's talk about that. Arctangent of 1 is inverse here. This is basically saying, when is tangent of theta equal to 1? That's basically what it's saying. So the first instance where tangent of theta is equal to 1 is where theta is pi over 4. All right, we do some cleanup here. 10 minus 6 is 4. My denominator is just 1 minus pi over 4. If I find a common denominator, I get 4 minus pi over 4. And this is obviously not 0, right? So we don't do L'Hopital's rule. We just plug in and try to get it down to a numeric answer. You can either leave like this, or if I multiply by the reciprocal to bring this messy fraction up top. Numerators together gives me 16. Denominator is 4 minus pi. But I think either form is fine. It's just a little bit cleaner here than here. Okay, let's look at number 4. Page 12. A cylindrical barrel with a diameter of 2 feet contains collected rainwater. The water drains out. It's not shown, but water is draining out. The ratio of the rate of change of the height h of the water in the barrel with respect to time t is modeled by dH dt. Okay. Where h is modeled, measured in feet, and t is measured in seconds. The volume is given by v equals pi r squared h. Okay, so let's look at part A. Part A says find the rate of change of the volume of water in the barrel with respect to time. So we're trying to find dV dt when the height is 4 feet. So we know the volume formula of a cylinder is pi r squared h. Now, the thing that is easier about cylinders versus cones is that we don't have to hold on to the radius variable. With cones, we had to, because when water is either going in or coming out, the radius and the height of my water level is changing all the time. But here, you can kind of imagine, right? No matter where my water level is, my radius is never going to change. So I can just go ahead and replace the r with a numeric value, since there's no need to hold on to a variable if it's never going to change. So V is simply equal to pi h. Okay, find the rate of change of the volume of water. So we're looking for dV dt. With respect to time, so that indicates to you that we're dealing with the related rates here when the height of the water is 4 feet. Okay, let's go ahead and find the derivative. V becomes dV dt, pi stays, and h becomes dH dt. Okay, we start inserting information in. We're looking for dV dt. We're looking for dH dt. So dH dt, we can insert from the top of the problem here. Okay, it says when the height of the water is 4 feet, so we can insert that 4 in for h and solve for dV dt. I don't want to forget about the pi here. So root 4 is 2, negative 2 pi over 10. Which reduced to be negative pi over 5. And we're talking about volume and time, so cubic feet per second. Part B, when the height of the water is 3 feet, is the rate of change of the height of water increasing or decreasing? So this is kind of a subtle way of saying, okay, is the rate of change, which is already dH dt, is the rate of change increasing or decreasing? So this is talking about the rate of a rate. This is referring to the second derivative of height. So we got to involve d2h over dt2, and then figure out at this point, is it positive or negative? If it's positive, then we know the rate of change is increasing. If my second derivative is negative, then I know the rate of change of height is decreasing. Okay, rate of change refers to d2h over dt2, so part B. Let's start off with dH dt, and we can build the derivative. Rewriting it as a rational exponent. So I'm trying to find the second derivative here. Go through power rule. Subtract 1 from the exponent. And then attach a dH dt. Every variable gets affected by time here. Make our substitutions here. I know dH dt is -1/10 root h. dH dt, -1/10. Get the h's to cancel out. I get negative or positive 1/200. So positive 1/200 is obviously positive, so I know that the rate of change is increasing. Okay, part C. At time t equals 0, the height of the water is 5 feet. Use separation variable to find an expression. So we got to do separation variables, solving differential equations. Okay, so here's part C. All right, let me get this set up and ready so that I can separate the variables. I'm going to cross multiply first. Okay. Negative root h dt equals 10 dh. So I want my h's on the left. It makes it a little bit cleaner here. Let me rewrite that. So at least I have dh and dt in their right places. I just have to figure out what to do with the 10 and the root h. So I want to leave the left side as bare and minimal as possible. I only want what's absolutely necessary. I'll divide the root h over, and I'll move the 10 over, make them swap sides, and they both end up in the denominator. Okay, so both sides are going to be requiring power rule, but we got to do some cleanup on both sides here. That root h is really dh over h to the 1/2. It's still not ready for power rule, right? We still got to bring that up to the numerator and make it h to the negative 1/2, and then we can do power rule. Once I bring the h up to the top, I can do power rule. I'll do some cleanup first, multiply everything through by 2, so I don't have to stare at that complex fraction there. Okay, at this time, I'd like to go ahead and start entering in and finding my C value. I know that at t equals 0, the height is 5 feet. Okay, 0 in for t, 5 in for h. Let's see if we can solve for c. All right, so now let's see if we can enter everything back in. I'll enter that root 5 into where I made that substitution. Let's see. Let's see, 2, 2. Square 5 equals C. Okay, if I square both sides. Okay, sorry, it looks a little different from the key that I was working from. Let me see. Oh, okay, I messed up here. This is really sitting at a 2. So to get rid of the 2, I need to multiply by 1/2. Okay, so I multiply by 2 instead of 1/2. Let me update that part. Okay, I jumped the gun here. Let me start from that point here. This h to the 1/2 over 1/2 is really a 2. And I multiply everything through without first cleaning up. Okay, so from here, if I divide everything by 2, it's a little bit cleaner here. Let me do that. Divide everything by 2. Multiply everything by 1/2. Okay, let me try again. Order pair 0, 5. Okay, back to my equation. I square both sides. There we go. All right, number 5. Okay, so let R be the region enclosed by the graph of g of x. H of x is the 6 minus 2, x minus 1 squared. So the 6 minus 2, this kind of reminds you of a parabola that opens down, right? You got the negative, you got the squares, so it's going to be a parabola. So you know that this h of x is referring to this part, right? This is more of a parabola shape than the other graph. And this negative 2 plus 3 cosine, that's going to be the one below. All right, so we're told to find the area of R. Remember, this is non-calculator, so we got to show all of our steps here. It looks like this is going to be a nice top minus bottom setup here. Okay, so area, top minus bottom. The top is the H, the bottom is the G. So I'll take my time to subtract those. And again, I know this seems tedious because normally this is a problem that we would want to put in the calculator, but we're going to do this by hand here. Okay, I'm going to full all this out because really I need to rely on power rule for a lot of this here. I guess we could have also done use substitution here, but I just decided to pull this out. Okay, 2's cancel out. All right, so the first few terms is power rule. The last term, we do have to go through use substitution there. So if we want, we can treat this like its own problem there. Our u value is pi over 2 x. And dx is what we want to also replace. Okay, let's see if we can do all of these. Let's do the calculus here. So every single one of these terms, I'm going to apply power rule as well as find the antiderivative of cosine. So 6 becomes 6x. Three times 2 is 6, 6 over pi. And then cosine turns into sine. We bring back our original variable. Now that we have our antiderivative, we can work in the bounds from 0 to 2. Okay, upper bound first. 6 times 2 is 12. 2 times 8 over 3 plus 2 times 2 squared. Plug in 2 in for x. I get pi. Sine of pi is 0. And then I can also subtract minus the lower bound, and all that is going to give me 0. Make sure I'm on the right track here. Okay. So 12 plus 8 is 20. 20 minus 16 over 3 is the same thing as 60 over 3 minus 16 over 3. Common denominator. I get 44 over 3. It's a long, tedious problem. Part B. Region R is the base of a solid. So let's say this is now the base of a solid. We're going to be building shapes on top of it. For the solid, at each of the x, the cross section perpendicular to the x-axis. Okay, so this is always going to tell us which way to draw our base. Is our base is going to be drawn vertically or horizontally? So this will tell us x-axis is horizontal, cross section perpendicular. That's going to force it vertical. And we don't have to worry about what that area formula is. We don't have to worry about, oh, is it a square or a rectangle or semicircle? It's already built in to us for us to use. So we know the volume of cross section looks like this, the integral from x1 to x2 of the area dx, whatever that area is. Sometimes we have to build it on our own. If it's a base, we would have to worry about, doing 1/2 squared, 1/2 base squared, or 1/4 base squared. But here it's telling us exactly what the area is. We don't have to go through the trouble of really even worry about how having to subtract those values. It's already given to us here. Okay, our bounds though is from 0 to 2. So this is a fairly straightforward use substitution problem. Make our substitutions here. No coefficients to keep track of. This will give us directly into natural log. Bring the original variable back. And then work in the lower and upper bounds. Upper bound first, then lower bound. This is perfectly fine, natural log of 5 minus natural log of 3, but you can also condense it to make it natural log of 5 over 3. All right, so those are all acceptable. Part C, it says write but do not evaluate an integral expression that gives the volume. So the nice thing, we only have to set it up. We don't have to worry about finding the actual volume. Find the volume of a solid generated when R is rotated about the horizontal line y equals 6. So y equals 6, 1, 2, 3, 4, 5, 6. So y equals 6 is going to be right there, right, basically skimming the surface of the curve. And we see that it's up against the curved surface. We know this is not going to be this method, it's going to be washer method. And because it's washer method, we have to draw in 2 radius. So here's my diagram that I drew here. Okay, so here's my curve. Here's my y equals 6. I know it's going to be washer method, so I draw 2 radius, one that extends from the dotted line all the way to the furthest boundary. And then I also need to draw small radius that will start from the center as well. This is my new center. This whole shaded region is going to be flipped over, rotated around that dotted line. So small radius is the dotted line, 6 minus h of x. So we build our r of x and g of x. Integral from 0 to 4, 0 to 2, pi big R squared minus little r squared. We only are asked to set it up. There's no need to do anything beyond that. All right, questions there? All right, number 6. Okay, functions f, g, and h are twice differentiable. Just means there's a smooth curve. It's going to be at power at least greater than 2 or higher. G of 2 equals h of 2 equals 4. The line 4 plus 2/3 x minus 2 is tangent to both the graph of x equals 2 and the graph of h at x equals 2. So if 2 graphs share the same or tangent, that means they must share the same slope, right? Share the same slope. So if I can find y prime, if I can find the slope of this y line, then I know what the slope of g of h is as well. So I know based off of this line has a slope of 2/3, right? Y equals mx plus b. And if this line is tangent to the graph of g and h, then it must skim the surface in a way that will make it share the same slope. So we can say this. Since the graph of h is tangent to the line y equals 2/3 x minus 2 plus 4, and this is a point slope form, slope being 2/3, they must share the same slope. H prime of 2 must also be 2/3. Okay, number 2, or part B. Let a be the function given by a of x, 3x cubed h of x. Write an expression for a prime of x, then find a prime of 2. So I want to find the derivative for a of x. I look at how this is set up. Looks like I'm going to need product rule to find the derivative of this expression, right? 3x cubed and h of x are completely separate functions outside of each other that are being multiplied. We got to go through product rule. F prime g plus f g prime. Okay, so we'll let f be the 3x cubed, the g be the h of x, and we just go through product rule. F prime times g plus fg prime. Right, 3x cubed becomes 9x squared, h of x becomes h prime. We make them alternating, taking turns, pairing function with its derivative with the other's derivative. And once we have the derivative, then we can start working towards our slope, replacing every x with 2, and see where that takes us. 9 times 4 is 36. H of 2 is 4. They told that to us. 3 times 8 is 24. H prime of 2 is 2/3, right? We found that. Then we're just trying to get it all down to a single number here. So 9 times 16 is 144. 3 times 8 times 2/3. We can get the 3's to cancel out. 8 times 2 is 16. 144 plus 16 is 160. Okay, part C, looks like they're referencing L'Hopital's rule, so we'll jump into that process. And I would be more careful than how I'm showing it. This equals is not going to be good for how you want to show your work. So do arrows that lead from one work to the other. Okay, don't use equal sign. Okay, so first thing we do is convince ourselves that L'Hopital's rule is good to go. Replace every x with h approaching 2. Sorry, x approaching 2, not h. Okay, replace every x with 2. I get 2 squared minus 4. That's 4 minus 4. That's 0. Denominator, I get 1 minus f of 2 cubed. F of 2, they told us at the beginning, f of 2 is... Oh, it says use this to find f of 2. Okay, so we don't know what f of 2 is yet. But we do know that L'Hopital's rule is going to be fulfilled. They're telling us that. So we don't even know we don't know what f of 2 is. We know at least is we're getting 0 over 0. So we move on. So we go ahead and we find our derivative. X squared minus 4 becomes 2x. 4 goes to 0. 1 goes to 0. And then f of x cubed, we got to go through chain rule here. Outside derivative times inside derivative. Bracket cubed becomes 3 bracket squared. That takes care of the outside derivative. And then the inside, f of x turns into f prime. A little bit of a chain rule. Okay, replace every x with 2. I get 4 in the numerator. I still am replacing 2 in for all the x's. I don't know what f of 2 is. but I'm going to just work around it. -3 times f of 2 squared times f prime of 2. Okay, here's the second part of part C here. Since h is continuous, we know that h of 2 must be equal to the limit as x approaches 2 of h of x. So we know that h of 2, which is 4, must be equal to this mess. So what if I just set them equal to each other, and I can kind of work backwards to figure out what this f of 2 is equal to. Cross multiply. -3 times f of 2 squared times f prime times 4. I divided that 4 over to the right side, equaling 1. Divide both sides by -3. Now we do know that L'Hopital's rule is satisfied, so this requires a little bit of detective work here. It's like, how do I know what f of 2 is? Well, I know that it fulfills L'Hopital's rule, so I must get, if this is going to work out, if this is going to fulfill L'Hopital's rule, then f of 2 must be equal to 1, right? 1 cubed is 1. That's the only way I can get that 1 minus 1 to 0. So I know that f of 2 is 1. So that's kind of tricky, trying to look at all these context clues to figure out, okay, I don't know what f of 2 is, but I do know enough to know this must be equal to 0. So f of 2 must be 1. And if f of 2 is 1, I can work backwards to solve for f prime of 2, divide both sides by 1. -1/3 divided by 1 is still -1/3. Now, kind of a tough one there. Part D. It is known that g of x is less than h between 1 and 3, and k satisfies is between g of x and h of x for between 1 and 3. Is k continuous? Okay, well, we know that g and h are continuous, and g of 2 and h of 2 is equal to 4. And we also know that the limit as x approaches 2 of g of x and h of x equals 4. So we're basically working out all of the conditions for continuity. We can conclude that the limit is 4 and the order pair is 4. So if our limit exists and if our order pair exists and they are not in conflict with each other, therefore it fulfills all of the continuity conditions. Our k of x function must be continuous at x equals 2. All right, it's a lot going on with these few problems here. Any questions? Okay, that's all I have. See you guys tomorrow for 2018 help session.
Thank you.
Thank you.
All right, thanks guys. Have a great day. Bye.